Okay, so we're going to go back and quickly finish up our case study from last week. So if you recall, last week we looked at this example of a linear regression on data for kind of finding a baseline for teaching evaluation scores. And our goal was to try and set up a per course, per instructor baseline based on non-teaching quality features. So for example, we want to be able to predict, let's say, what would the typical score be in a class taught by a female instructor? Or what would the typical score be in a class with a large number of students, or a class that's a lab? We want to kind of create a more fair baseline against which to evaluate actual teaching performance or actual teaching scores. And what we said last week was that we were kind of surprised that there were some features that appear to be important in our model that weren't really important. So first of all, when we say there are features that appear to be important, how can we tell if a feature appears important? What does it mean when we say, let's say, that whether or not the picture is black and white appear to be important to the model? So one of those things was large coefficient. We found that there were some features that were not informative, or that we expect to be uninformative, that had a non-zero coefficient. That's similar to what we just looked at today, where we saw that when we had uninformative features, the linear regression would still find a non-zero coefficient on them because of that noise. And then in addition to finding that features had non-zero coefficients when we didn't expect them to be informative, we also found that in many cases, the model performance was worse without those features than it was with those features. Right? So we found, for example, that let's say the test R squared with most of the features we don't expect to be important removed was only 0.06. But with those features, it was much higher. So whenever we have features that we expect to be uninformative, but that end up kind of helping the model, what is that a potential sign of? Okay, so we said in week 1 that very often if you have data leakage, then your model will end up learning from features that are not expected to be important. For example, we said in this example of COVID chest X-ray data, so these researchers found that their model was learning from features like the pixels in the corner of the images where the shoulders are, rather than from the lungs. This is often a potential sign of data leakage when your model is learning from features that you don't expect to be important. So how can we evaluate for this data leakage? How can we know whether we have some leakage going on here? Well, we said that we have this concern here that if we look at some examples from the data, especially data for some features that were more informative than we expect, we can see that we have what appears to be the same instructor teaching many instances of a course or many rows in the data. For example, here we see many rows that appear to be of the same instructor, who's a teaching track professor, minority male, trained in an English-speaking course, 50 years old, and has an attractiveness ranking of 3.33 on average, with a not formal photograph in color. So we have many instances where the same instructor is teaching the same course multiple times. Let's take a closer look at that. Now, we're going to try and add an instructor ID to every row in the data frame. The data does not include a real instructor ID, But we can actually still uniquely identify every instructor by looking at the combination of instructor-specific features. So I'm creating this instructor ID column, which is just a concatenation of all of the instructor ID feature, all of the instructor-specific features. And let's notice here that okay, so let's notice here there are a total of 95 unique instructor IDs, meaning if we concatenate rank, ethnicity, gender, language, photograph features, age, and attractiveness ranking, we get 95 unique values. Does anyone remember how many instructors are supposed to be represented in this data set according to the paper? So according to the published paper, there were 94 instructors represented. The data set we're using is a slightly modified version of the one in the paper, which could account for that difference. But it seems pretty clear that by concatenating all these instructor-specific features, we've been able to uniquely identify every instructor. Let's see if this situation here, where one teacher teaches many courses, is kind of unusual or if it's a norm. So we're going to plot the frequency with which each instructor ID appears in the data. So on the far side here, we see there are some instructors that teach as many as 13 of the rows in the data. And we have, let's say, a handful of instructors that only teach once. And most of the instructors are represented more than once in the data. Randomly sample some of our data into a training set and some into a test set, it's very likely that the same instructors will appear in both the training set and the test set. Is that a problem? Okay, why might it be a problem for the same instructor to be in both the training set and the test set? Well, let me give you another example. Okay, so suppose instead of this data set, I had a data set with exactly one feature and one target variable. Okay. The feature is an instructor ID. So maybe I have instructor ID. I'm going to make it categorical. So it's not going to be, it's not going to be ones. It's going to be, let's say, J, A, F. So these are, let's say, instructor IDs. And then the target variable is going to be the same. It's a teaching score. So maybe in one course, J got a 4.65. In another course, he got a 4.0. A got a 2.3 in one course, a 3.1 in the next. Instructor F got a 4.9 in one course, a 4.5 in another course, etc. Okay. And then I'm going to train the model on this data set. So the only feature that the model is learning from is instructor ID. And then I'm training it to predict the evaluation score. First of all, do you think that the model will be able to kind of have some informative prediction of teaching evaluation score just from knowing who the instructor is? Okay. Let's say the kind of department average is a 4. Okay, so department average is a 4. We're going to use a model to try and predict a different average for each instructor. Can we do that? So this model is going to learn the per instructor average. right? So the model is going to learn, okay, for instructor J, the average evaluation score is 4.3, whatever. For instructor A, the average evaluation score is 2.8, not 2.8, but something, right? So we would be able to train a model to predict the average evaluation score for each instructor if we gave it a data set of instructor IDs and scores, right? That's just a pretty simple model. So a basic linear model should be able to do that. Does anyone agree, disagree? So the concern is that if a model can do that, if it could predict, let's say, a per instructor average evaluation score, well, what if that's exactly what our model is doing? So our model might not be learning, let's say, a true relationship between, for example, attractiveness and teaching evaluation score. Maybe it's just learning like, oh, hey, I see a row that says 50-year-old male instructor teaching track, non-minority and attractiveness ranking of 3.33. I know who that is. That instructor usually has an evaluation score around 4. So instead of learning a true relationship, it's really just memorizing the individual instructors who happen to be in the training data. Let's see how plausible that is. Okay, so I'm going to create a plot here that for each instructor shows all of their evaluation scores in the data set. Okay. And I've ordered them by their average evaluation score. So we can see that each instructor has kind of like a typical range of evaluation scores across all the courses they teach. Okay. So imagine we had this data set where, okay, maybe I'm going to hold out a few examples as test points. Okay, so this is a test point. 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 Given the instructor ID, right, and given all the other points as training points, we can kind of expect that this model should be able to predict the test points pretty well, right? Because the instructor can kind of learn what the typical is for each, the model can learn what the typical score is for each instructor, and then just predict that for your test points. Okay. So what if instead, for the training data, okay, so for the test data, I held out this instructor, this instructor, this instructor, and I gave all the other data to the model for training. In that case, the test data will be instructors that the model has never seen before. Okay. So maybe the model has never seen instructor F, instructor G, or instructor K. Do we expect that the model should have any way to predict the average score for those instructors? So if the model was learning some kind of fundamental relationship between things like gender, attractiveness, ethnicity, and score, then the answer should be yes, right? If the model was learning some fundamental relationship, then if we give it examples of new instructors, it should be able to predict at least some part of their teaching score. But if the model is not learning any fundamental relationship, and instead it's just memorizing individual instructors who are in both training and test data, then the model would fail to generalize to new instructors it has never seen before. So we're going to actually try this. I just described 2 ways of splitting up the data into test and training. And if you remember from our lesson on this, okay, so in our lesson on Tuesday, we gave some examples of splitting up the data into training and validation. So we're going to do that here. Our original example was just kind of like a shuffle. And now we're going to do a group-wise split, where let's say each individual instructor is a different group. So in every fold, an individual instructor will be in either training or test, but not both. And let's see how that works. So first I'm going to do a k-fold evaluation on a random split. And I'm computing the mean metrics in each case. So here's the mean R squared for the training data. Here's the mean R squared for the test data. So there's a small difference, but the model does appear to have some predicted value because there's a positive R squared even for the test data. Now we're going to do it again, but this time we're going to divide the data so that each individual instructor is in the training data or the test data, but not both. And here is our mean performance again. So the mean R squared for the training set is 0.22. The mean R squared for the test set is actually negative. I'm going to plot it, but my plot is limited to the range 0 to 1. So it just shows that the test R squared, the test evaluation shows that the model has no predictive value. Okay, based on this analysis, do we think this model can predict teaching evaluation scores of new instructors? So we expect that it could not. The model initially appeared to have some predictive value when we used like a random training test split. But it turned out that this this evaluation score was kind of a mirage that was caused by data leakage. The model appeared to have predictive value, but because of data leakage, we had an overly optimistic test error. And once we kind of correct that data leakage, we find that the model actually has no predictive value at all. So what went wrong here? Well, we actually saw two problems here. The first problem was that the model was memorizing individual instructors from the training data and not learning a general relationship between teachers and target, between features and target. So the first problem was overfitting. Now, usually when a model is overfitting, you can tell that it's overfitting because it has great performance on training data and bad performance on test data. In this example, we didn't see that. Why not? Because of the data leakage. Because of the data leakage, the model had overly optimistic error on the test set. So it looked as if the model would generalize to new unseen data, but that was only because of leakage. So we weren't actually evaluating the model on new unseen data. So we saw that when we did a correct evaluation without the leakage, we had learned that in fact the model does not generalize and does not have predictive value. Okay, so that about wraps up today. Are there any questions? Okay, very good. I will see you all